Hello, my dear students. Let me continue the computational linear algebra. The characteristic roots, we call it as the eigenvalues. Let V be a finite dimensional vector space. Whenever we use the word finite dimensional vector space, that means it is a basis. That means vector space is a basis. Okay. Let V be a finite dimensional vector space over a field F over a field F if T is an element of subalgebra, that is FE, then lambda belongs to F. Lambda is a scalar. Whenever it belongs to F, that means a scalar. If lambda belongs to F, is called as eigenvalue of T. If lambda I minus T is singular, you know the meaning of singular. If it is not regular, then we call it as singular. In other words, we define like this. Uh, Lambda, the scalar, lambda belongs to F is eigenvalue of T belongs to Fv if and only if for some non-zero vector in vector space V, Vt, that is image of V under T, that is Vt is equal to lambda V. This is the definition of what? The eigenvalue, the characteristic roots. Okay. Let me take one lemma. The statement of the lemma is like this. If lambda belongs to F is a characteristic root, the eigenvalue of T belongs to Fv, then for any polynomial Q of x belongs to set of polynomial rings, and we denote it like this. F of x should be inside the square bracket. Q of lambda is a characteristic root of Q of t. This is the statement of the lemma. The proof of this lemma is very simple, but here we have to make use of the definition of what? The eigenvalue of t. If lambda belongs to F is a characteristic root of t, by definition of characteristic root, the eigenvalue, there exists a non-zero, this word is very, very important. There exists a non-zero vector V in vector space V such that Vt equal to lambda V. This is by definition of eigenvalue of T or the characteristic root of T. Let me consider Vt2. Don't read this one as T square. We have to read it as Vt2. Vt2, I'll rewrite this one as Vt of T. T2 can be written as T into T. So Vt of T, again by definition we replace Vt by lambda V and grouping, that means taking lambda outside, we write it as Vt. Again Vt means lambda V. This is same as writing lambda square V. That means if Vt2 is equal to lambda square V. In general, Vtk is equal to lambda to the power kv for all positive integer. That means k should be positive. K is a positive integer. Let me take a polynomial and we denote that polynomial by the notation q of x. Let q of x is a polynomial in x of degree k, where all the alphas are scalars. What I do now, I replace x by t. We get a polynomial of this type. Q of t equal to lambda naught plus not lambda naught, Q of t equal to alpha naught plus alpha 1t plus alpha 2t2 and so on. I'll multiply both sides by, left multiplication. I will multiply both sides by a non-zero vector v. We write like this. Again taking v inside and using the definition of what? Using the definition of eigenvalue value of t, I mean the characteristic root of t. Again, taking v common to the right hand side, we replace this bracket by a polynomial in lambda, that is q of lambda of v, where q of lambda, I mean polynomial with respect to a scalar lambda, therefore it belongs to f. Now, taking all the terms one side, what we write? We write it as v dot of q of t minus q of lambda equal to 0. By statement, it should be singular. If it is singular means it is not regular. Therefore, the q of lambda is a characteristic root of what? Q of t. This completes the proof of the lemma. Very simple. Let me continue. The another definition, characteristic vector. To define a characteristic vector, we need a non-zero vector. To define eigenvalue of t or the characteristic root of t, we need a scalar. Here we need a vector. An element, I mean a non-zero vector, is said to be a characteristic vector of t belonging to the characteristic root of scalar, that is lambda, belongs to f. Same condition holds good. Vt equal to what? Lambda v is said to be what? The characteristic vector. Let me clear one point. To define the characteristic vector, we need a vector. For each vector, we have a scalar. To define a characteristic root, we need a scalar. And for each scalar, we have a vector. Okay. Let me prove one theorem. The statement of the theorem is like this. If all the lambdas, I mean lambda 1, lambda 2 and so on up to lambda k in f are the distinct characteristic roots of t belongs to f v, then v1, v2 and so on vk are, I'm sorry, it is not a characteristic roots, it should be a characteristic vector, it should be the characteristic vectors of t belonging to lambda 1, lambda 2 and so on up to lambda k respectively. Then we have to show that all the v's, I mean the non-zero vectors, are linearly independent. Before I prove the theorem, let me recall the definition of linearly independent. To define linearly independent, we need a scalar. Okay, we need a scalar alpha 1, alpha 2 and so on alpha k such that the linear combination of the vectors, that means alpha 1 v1, alpha 2 v2 and so on alpha k vk equal to 0. See that all the scalar values should be 0. If all the scalar values take 0, then the vectors are said to be linearly independent. If at least one scalar is not equal to 0, that means the vectors are linearly dependent. Independent means all the scalar values takes 0. That means all the scalar values are equal to 0. If they are dependent, at least one scalar is not equal to 0. We prove this theorem by using the induction method, I mean mathematical induction. Let me take one vector. If we have only one vector, the result is very simple. There is nothing to prove because if lambda 1 is the characteristic root of t, by definition we write it as v1t equal to lambda 1 v. Since v1 is a non-zero vector, that means since the vector is a non-zero, that indicates what? Lambda 1 must equal to what? 0. What it shows? This shows that the vector is linearly independent. If we have more than one vector, what will happen? We prove this result by contradiction method. Contradiction method means opposite of that. That means I will take linearly dependent. Instead of linearly independent, I have to take linearly dependent. If the vectors are linearly dependent, by definition, you know the definition of linearly dependence. By definition, there exist scalars alpha 1 to alpha k such that the linear combination of the vectors equal to 0. But here, not all the scalar values are 0. That means at least one scalar is not equal to 0. Okay. Let, let me take another set of scalars. B1, B2, beta 1, beta 2, beta k are the non-zero scalars. And let me introduce one important point here. I will explain this one later. At the end, you will come to know the meaning of this one. Let all the betas, I mean beta 1, beta 2 and so on, beta k are the non-zero scalars and they are the smallest set such that the linear combination of the vectors can be written as beta 1 v1 to beta j vj equal to 0. And I'll denote this representation by 1. We know by definition, VIT is equal to lambda I VI. I takes the values 1 to k. Let me operate the linear operator, that is T, both sides, operating T both sides and taking T inside and using the definition of what? Characteristic vector. So we replace it by what? Lambda 1, beta 1. Lambda 1, beta 1 is a scalar. Lambda 2, beta 2 is scalar. Lambda j, beta j is a scalar. I denote this representation by 2. What I do now? Second result minus what? I will multiply the first result by lambda 1 and simplifying. What we get? We get expression of this type. Since all the characteristic roots are distinct, that means they are different. Since they are different, lambda j minus lambda 1 is not equal to j, not equal to 0 for all j value is greater than 0. Okay, what it indicates? It indicates the scalar is not equal to 0. Scalar is not equal to 0 means the vectors are linearly dependent, which is contradiction. Therefore, the vectors should be linearly what? Independent. This completes the proof of the important theorem. Now, let me continue. The matrices. You know the definition of matrices? It is a rectangular array. There you will see the rows and columns. Let V be an n-dimensional. Let V be an n-dimensional vector space. That means the set has n number of vectors and they form what? Basis, because we have here we see the word dimensional. Let V be n-dimensional vector space over a field F, and let me take the vectors. Since it is n-dimensional, that means n vectors. Let v1, v2 and so on be the basis of a vector space V over a field F. Then for an element T belongs to Fv, what we have? We have the elements of this nature. v1t, v2t and so on, v and t belongs to what? The finite dimensional vector space, that is V. What I do now? I rewrite v1t as a linear combination of the vectors v1 to vn. That means expressing listen to my words carefully, expressing v1t as a linear combination of the vectors like this: alpha 1 1 v1, alpha 1 2 v2 and so on, alpha 1 in vn. Similarly, expressing v to t as a linear combination of the vectors, say v1 to vn, we get like this. At the end, expressing v and t as a linear combination of the vectors v1 to vn. And writing this one in the matrix form, that means taking the coefficients of v1 in the first column, coefficients of v2 in the second column, coefficients of vn in the last column. We get a matrix of this nature. We denote it by what? M of t. That means matrix of what? Matrix of T, where T belongs to subalgebra, that is A of V. Matrix of T where T belongs to the subalgebra, that is what? A of V. Okay, using this matrix, we can prove some important results. I mean, I'll take some examples. The examples are very simple, provided it should be provided the vector should be the basis. Okay, if they are basis, then